This is Physical Science 2, Chapter 17, Part 4 on Weather and Climate. In this portion of the video lecture, we will be discussing Earth's changing climate. Now remember, seasonal changes throughout the year. The key factor for there is the hemisphere tilt. It does not have anything to do with our distance from the sun. We experience seasons because if our hemisphere is tilted towards the sun, then we will experience summer. If our hemisphere is tilted away from the sun, we will experience winter. So that long-term summer-winter changes over a very long period of time. That is climate. So when we take a look at what type of evidence Earth has to give us about ancient climates, we can find this information drilling into the ocean sediment and taking a look at ocean crust cores, as well as taking a look at ancient ice cores as well. So cycles of glaciations or ice ages represent long-term climate change on Earth. And about 3,000 years ago, give or take, we kind of established what we have right now as the general world climate. You can see there the climate swings of the past 12,000 years. The Earth has been a lot chillier on average than it is today, and it's also been a lot warmer on average than today as well. And remember, we talked about the biogeophysical system and how that influences climate. So there's a couple of different ways that we can get climate change on Earth. We have some Earth-caused reasons, things like mountain building. We talked about, for example, the Lee rain shadow effect in our last section. Over time, as the mountain builds, that will change an overall climate of an area as well. As the continents move around, we have different climates based on their location on the planet. Major volcanic eruptions have also caused some short-term climate change. With very major volcanic eruptions, we get a lot of that ash in the air, which can block sunlight for a very long period of time, causing temperatures to be cool for a short-term change. Then we have some kind of orbitational or sun-caused reasons for climate change. There is variations in the amount of solar radiation that the sun puts out. We've discussed sunspots. The fewer sunspots, the warmer the radiation coming from the sun. And if there were any changes in our orbit, if we were closer or farther away from the sun, as well as our tilt, that can overall take climate change and put it in the long term. And of course, there is the fact that people have influenced global climate change. The amount of which the human factor has influenced global climate change is up for debate, but we do have evidence that shows that what we are putting into our atmosphere, what we are putting into our soil and groundwater is at a slow pace changing the Earth's climate. The carbon cycle is a main concern for global climate change. This is the exchange of carbon between land, air, and water environments. We have carbon taking place and exchanging in photosynthesis and respiration, as well as decomposition, since we are all carbon-based life forms. The carbon cycle is affected from human activities, mostly due to fossil fuel burning and deforestation. If there is not as much plant life to take up that carbon dioxide will remain in our atmosphere. And if you remember, carbon dioxide is one of those gases that tend to trap infrared or heat energy near the surface of the Earth. So carbon dioxide contributes to the greenhouse effect, but if, remember, we get too much carbon dioxide in the atmosphere, we get a runaway greenhouse effect, which could lead to global warming. So global warming would have to be an increase in the average global temperature of the Earth, not just certain regions becoming hotter or colder, but indeed the whole planet increasing in temperature. We've talked about the ozone layer. Remember, the ozone layer is in the upper parts of the stratosphere, and it acts kind of like the Earth's natural sunscreen. It helps protect us from the ultraviolet radiation that the sun puts out. The ozone hole, the largest damage to the ozone is above a place in Antarctica called Halley Bay, which seems odd. If you would think, why would the damage to the ozone layer be over Antarctica? There isn't anyone that lives there except for some scientists that reside there on a temporary basis for research. Since Antarctica isn't the one that's polluting, why do they get the damage? Remember, we have global wind patterns that influence our climate. And when we put chemicals and pollutants into the air, those global wind patterns will also carry those pollutants to different places. And generally where this is settling is in the southern hemisphere. Now, there has been international agreements made to limit the production of what are called chlorofluorocarbons, or CFCs. CFCs are a class of chemicals that are extremely damaging to the ozone layer, and they are in a lot of common items that we use. Aerosols, for one, have a lot of chlorofluorocarbons. One molecule of chlorofluorocarbon, or CFC, can destroy anywhere from 10,000 to 100,000 molecules of ozone. And because the ozone hole is precious and it helps keep us protected from the radiation from the sun, we do need to be aware of its damage and at least start to repair it. Here's a comparison map from one of the first bits of data that have been collected about the ozone layer in the late 70s, early 80s. And then you can see here in October 2015, that was the last, the most current picture that I could find of this. So the greens and the blues are good and solid. The yellows means that it's thick. The purple and the dark blue, however, means that that's where the hole is. So you can see the drastic change that's really taken place over a little over 30 years. The land surface, we've made a lot of changes to the land. We've drained wetlands and we've paved a lot of surfaces with concrete and asphalt. We've cleared fields for agriculture. We have, in some cases, because of our damming of rivers, we've caused what's called desertification, or making a land more desert-like. When we change the surface, that will influence that biogeophysical system over time, and that can change our climate as well. When we take a look at some global phenomena that can alter our weather patterns for a very short term, we can take a look at El Nino and La Nina. El Nino is a warming of the Pacific Ocean. This happens about every 3 to 5 years. What occurs is the trade winds near the tropics, they slow down and they weaken at the equator, meaning that there's more direct sunlight that's being able to warm those waters there. And so that can alter global weather patterns for a very short term. And La Nina is the opposite. This is when the trade winds strengthen at the equator. So there's a cooling of the Pacific Ocean every 3 to 5 years. And so El Nino and La Ninas work opposite of each other and can cause kind of a short-term weather change. This has been Physical Science 2, Chapter 17, Part 4 on Weather and Climate.